In this problem, we have two rods. The first one AC, and we have a color that's pinned to AC at point C. And this color moves along this other rod that is pinned at point B. And at this instant shown, we know that this angle right here is 45 degrees, and we also know the angular velocity and acceleration of this rod right here. So we have the information here. And we need to determine the angular velocity and angular acceleration of rod AC. So for this problem, because the collar is pinned at point C with the rod AC. However, the collar is not pinned along this rod. Therefore, the collar moves along this rod, and we already know the orientation of the relative velocity of the collar on this rod. It has to be either in this direction or in this direction. And at the same time, because point C belongs to rigid body AC, and we know that rigid body AC, this rod is pinned at point A, therefore it is rotating at about a fixed axis. Therefore, we also know the absolute velocity direction, VC, has to be in this direction. With this information, we're going to solve this problem using the relative motion analysis with rotating axis. We're going to choose the rotating axis to have the origin at point B. Therefore, the rotating axis rotates with this rod right here. We have the option, we can choose the x-axis to be along this direction, x and y. But for convenience, that's just my preference, we're going to actually choose the x and y axes still along my conventional horizontal and vertical direction. So that is the rotating coordinate system. Also, currently, it's coincident with the fixed coordinate system, capital X and capital Y. The difference is capital X and capital Y coordinate system does not rotate, but the small case X and Y coordinate system rotates with this rod. So now let's write down several known parameters. For example, we already know that the velocity of point C has to be in this direction. Therefore, written in vector form, Vc as a vector equals to magnitude Vc I. Also, we know that the relative velocity of this collar along the rod has to be in this direction. This is the relative C with respect to B, xy within the rotating xy coordinate system. Therefore, Vc relative to B, xy must equal to the magnitude Vc relative to B times the unit vector. This unit vector points from point C to B. Therefore, this is the unit vector from C to B. And according to the coordinate system we set up, which equals to the position vector r from C to B, or B relative to C divided by its magnitude. And r, B relative to C, equals to 1, because this is 1, I, and then vertical down by 1 meter as well, minus j, divided by the magnitude is square root of 2. So this equals to Vc over B times square root of 2 over 2i minus square root of 2 over 2j. So that's what we know about Vc, the absolute velocity of point C, and the relative velocity of C along the rod BC. We do not know the magnitudes, but we do know their direction. Remember, here is a hint here. We do know the direction. And then moving on, we're going to write these two, angular velocity and angular acceleration, in vector form as well. They are both clockwise, therefore omega. This omega is the it's capital because it represents the angular velocity of the coordinate system, the rotating coordinate system, which is the same 4 radian per second negative k, so negative 4k. And then the time derivative, which is the same as the 2 radian per second squared alpha, right here, angular acceleration. This represents the angular acceleration of the rotating coordinate system, and that is negative 2k. What else? We also might need the relative position. We need a relative position vector from A to C. So this is R, C relative to A, and that simply equals to 1j positive because it's vertical up. And also we're going to need the relative position vector of point C with respect to B, therefore it's from B to C. So that is RC with respect to B, that equals to negative 1 along the x direction, so negative I, and then vertical up by 1 meter, so J. So at this point, we have written down several things we kind of know. You don't have to do this work ahead of time. You can start evaluating them as you need them. But for me, I just know that I will need to use them. So I write them over here for a quick reference. Now we're ready to write our relative velocity equation. So for point C, that is, the color C that moves along the rod BC, we can write its velocity. So VCI is what we know earlier based on rigid body AC. But in this rotating coordinate system, VC vector equals to VCI equals to VB, the velocity of this point right here, plus omega cross R C relative to B, and then plus the relative velocity xy. So this part right here is what we're familiar with. This is how we determine VC if C also belongs to rigid body BC. However, in this case, C does not belong to rigid body BC. Therefore, we have this portion plus another portion, that's the relative velocity of C along in the rotating coordinate system. So now VB equals to 0 because point B is pinned, and then omega is negative 4k cross RCB is right here, negative I plus J. And then VCB, we have the magnitude multiplied by its unit vector that gives its direction. So we can evaluate that. K cross I, so we can do a little coordinate system for help. K cross I according to right hand rule equals to positive J. So you roll your 4 fingers on your right hand from K to I, your thumb points to J. So 2 negative signs cancel each other out. So that is a positive J. K cross J equals to negative I, but then we have another negative sign, so that is a positive I. Plus square root of 2 over 2 VC over BI minus square root of 2 over 2 VC over BJ. So now we are ready to evaluate our scalar unknowns. We have 2 scalar unknowns, VC and VCB. So we separate the I and J components. For the I component, on the left hand side we have VC, on the right hand side we have 1 multiplied by 4, so that's 4J plus 4I here. So we have 4, and then plus square root of 2 over 2 VC over B. For the J component, on the left hand side we have 0, on the right hand side we have 4, this one right here, minus square root of 2 over 2 VC over B. So we have 2 scalar equations two unknowns. We can solve for VC easily by adding these two equations together. Plus sign, minus sign cancel each other out. Therefore, we can easily solve that VC equals to 8 in the unit of meter per second. Direction is in this direction. However, we are going to use VCB as well in the next step to calculate the to calculate the angular acceleration of rod AC. So at this point, might as well evaluate that, and that equals to 5.66, and then in the vector form, so VC equals to vector equals to 8I. In vector form, VCB equals to 5.66 multiplied by its own unit vector, and that eventually equals to 4I minus 4J in the unit of meter per second. So now we have determined VC, and because VC equals to omega AC times this radius of 1 meter, so VC equals to omega AC times 1 meter. Therefore, omega AC can be determined to be 8 radian per second. We can determine its direction in a manual way, so the direction is going to be clockwise. So that answers the first half of this problem. Now we move on to the second half to determine the alpha AC, angular acceleration of rod. For that, we're going to use the acceleration equation, again for relative motion analysis using the rotating coordinate system. So AC actually can be determined from rigid body AC first. So the acceleration of point C can be determined by recognizing that point C belongs to the rigid body AC. Therefore, it will have two components. One is the tangential component, the other is the normal component. So the tangential component equals to alpha AC, so basically AC cross R C over A, and then the normal component is omega AC squared RCA. So you can say that here we should have a AA here as well, if you remember the equation, but in this case AA is simply 0 because point A is fixed at the pin here. Okay, therefore point A doesn't have acceleration. So from here we can determine AC to be negative alpha AC I minus 64J. So we don't know it for certain, but this is the best we can get. And in this expression, we only have one scalar unknown, which is alpha AC. Now, using point B, the equation is for relative motion analysis using rotating axis, AB vector plus omega dot cross R C relative to B minus omega squared R C relative to B plus the 2 omega cross V B relative to C X Y eventually plus A C over B X Y. So this part right here is the acceleration of point C if point C also belongs to rod BC, which is not the case, okay? Because point C, color C moves along the rod BC, therefore we need to add this additional components. So this one right here is the Coriolis acceleration, and this one right here is the relative acceleration of color C along the rod BC. So let's start to fill in things that we know. We know that AB is 0. Therefore, this becomes omega dot, that is the angular acceleration of the rotating coordinate system. We determined that earlier to be negative 2k. This is a relatively long problem, so I have to move up and down. Hopefully you can still follow. So negative 2k cross RC over B. We've done this from the previous step already. And then omega is negative 4k, so this is simply negative 4 squared times negative I plus j, again RC over A. Sorry, RC over B. This right here. And then plus 2 times negative 4k cross VBXY was determined here, remember? So that is 4i minus 4j. For the ACBXY, again, the relative acceleration of C along rod BC has known direction. It has to be along the orientation of the rod. Therefore, it has the same unit vector as VCBXY. Therefore, we can basically use this part right here, just write similar thing. So we will have plus AC over B, just changing the velocity to acceleration, same unit vector, square root of 2 over 2i minus square root of 2 over 2j. So after we evaluate the right hand side, simplify, we have negative 14i minus 46j plus square root of 2 over 2ac over bi minus square root of 2 over 2ac over bj. Therefore, now we're ready to equate. I know it's a lot of math, probably got lost. We're ready to equate this left hand side to this right hand side. Remember, we got this from member AC. We got this from the relative motion along member BC. And then we compare them, realize that we only have two scalar unknowns. Now we can set up two scalar equations and solve for both of them. So for the I component, on the left hand side we have negative alpha AC. On the right hand side we have negative 14 plus square root of 2 over 2 AC over B. For the J components, on the left hand side we have negative 64. On the right hand side we have negative 46 minus square root of 2 over 2 AC over B. Two equations, two unknowns. Again, if we simply add these two equations together, we can solve for alpha AC. Alpha AC is negative 4 in the unit of radian per second squared. But if you want to solve for AC over B, it equals to 25.5, which means that the acceleration, relative acceleration as a vector equals to 18i minus 18j in the unit of meter per second squared. Therefore, this is what we were asked to solve, alpha AC and omega AC. So alpha AC is also, it's actually in this case also clockwise. Remember, for the omega AC, we determine the direction manually. For alpha AC, we actually determine the direction, this negative sign, mathematically. Either way, both of them are clockwise, and that's angular velocity and angular acceleration of rod AC. We solved for the absolute linear velocity and linear acceleration. Well, actually, the not yet, but linear velocity for the color as well. If we want to, we substitute alpha AC into this equation. Therefore, we can solve for the linear absolute acceleration of point C as well. That's actually not too difficult to do. So AC equals to 4i minus 64j meter per second squared. That's the absolute linear acceleration of point C.